Okay, so this talk is based on with the Max, which is not in public yet, but it's almost finalized. And this is the kind of the table of contents for today's talk. Okay, so to motivate this theory, let me start with the brief the Liouville equation. So let's be Hamiltonian affiliated to a von Neumann algebra A. The algebra describes the given physical system. So in quantum mechanics, the density operators evolve according to this Liouville equation. And the equation, we take the commutator with the Hamiltonian H, and we can note that this L sub H, the Liouville operator, assigns operators to operators, and physicists refer to this kind of operators as super operators. And as you can see, we are in kind of the setting we need to choose a von Neumann algebra describing the given the physical system, and this kind of algebraic approach is useful in many theory, like the Bratelli-Robinson the description of the statistical mechanics in the thermodynamic limit in the two volumes of books, and then the Giuseppe and Max's response theory in the abstract algebraic setting. So the good aspect of this algebraic approach is that, well, that this makes the mathematical description for various systems rigorous, but the bad aspect is that, well, this abstract setting, operators in this setting are usually the unbounded operators. So we need to concern about the domains whenever we come. So we need to impose a lot of technical assumptions on operator, which are difficult to verify for concrete models. So, well, meanwhile, there's many kind of the pseudo-differential theory in the various mathematical setting. Well, but the common aspect of all the pseudo-differential theory is that there is the way of assigning the functions, which are usually called symbols, to operators, and it enables us to translate the properties of symbols to associated the pseudo-differential operator. So we ask the kind of this question. So if we can regard the density operators and the Liouville super operator as kind of the pseudo-differential operators, then we expect that we could the list of technical assumptions in the algebraic setting. And for the density operators, of course, there is a nice classical pseudo-differential theory, but there has been no rigorous description of the pseudo-differential theory for super operators so far. So the goal of this talk is to introduce the newly constructed pseudo-differential calculus for super operators, which is a natural receptacle for the super operators such as Liouville, the super operators. Okay, so to this end, let me briefly explain about the magnetic file calculus. In this talk, we will work on the charged particle moving in RD with the magnetic field B with the vector potential A. And in order to prevent the functions we are working on is not kicked out from the function space that we desire. We impose some technical assumptions on the magnetic field and on the vector potential A. The assumption PB means that all components of the magnetic field is the uniformly polynomially bounded smooth function, and all components of vector potentials are the polynomially bounded smooth function. And the bounded assumption means that the first assumption is replaced by the assumption that all components of the magnetic field is the bounded smooth function. And we will denote the phase space of RD like this. And the elements of phase space will be denoted like this. So here the X, Y, Z means the space components, and the psi, eta, zeta are the momentum components. Here, I think I forgot to write the star here. And we equip the phase space with the standard symplectic form defined like this. Okay, and we also introduced the small parameters which quantifies the coupling of the charge to the magnetic field. So we quantified by the small parameter lambda, and we also introduced the semi-classical parameter epsilon. And these kind of the small parameters are crucial for asymptotic expansion arising in the study of the semi-classical limits, which is useful to study the system subjected to the external perturbation. And in the magnetic setting, the Bayesian building block observable are the usual position operators and the kinetic momentum operators. Here, the A denotes the vector potential A, and these the basic building blocks satisfy this commutation relation. The aspect which differentiate the magnetic setting from the non-magnetic setting is that the second relation. In the magnetic setting, the kinetic momentum operators is no longer commute. And by using this, the position and kinetic moment in the magnetic file system by using functional calculus like this. Okay, and with all this preparation, now we can define the magnetic file quantization of the symbol F is defined like this. Here, the F sub sigma F means the symplectic Fourier transform of F, and this is the magnetic file system introduced in the previous page. And if we define it like this, it enjoys a nice gauge covariance property like this. Okay, and what happens if we compose two magnetic pseudo-differential operators? If we compose two magnetic pseudo-differential operators, then it again becomes the magnetic pseudo-differential operators associated with this symbol. Here, the exponential factor, the gamma B means the magnetic flux through the certain triangle. Okay, and we can further extend the definition of the magnetic file product to the symbols more general than the Schwarz class functions. Well, this is also the very well-known definition. The class of Hermander symbols of order M is defined like this. And if we take the magnetic file product of the Hermander symbols of degree M1 and M2, then it yields another Hermander symbol of degree M1 plus M2. All right, and there is also the settled theory of the asymptotic expansion of the magnetic file product with the two small parameters I explained in the previous page. So if we take the Fermander symbols like this, then their product can be expanded like this, where all these terms belong to the appropriate Fermander symbol class, and to ensure that this term approximates the given magnetic file product. It can be also shown that the remainder, the semi-norm as a Fermander symbol of the remainder term can be made sufficiently small if we take the n large enough. So this is kind of the practice portion, the magnetic file calculus. And for details, I refer to the Max YouTube mini course uploaded on the last week. Okay, so now let me move on to the pseudo-differential, the super operators, and to introduce them, I introduce you some new notations. To introduce the pseudo-differential super operators, we need to deal with the functions on the doubled phase space defined like this. And the elements of doubled phase space will be denoted like this. Here, the L and R stands for the left and right. And so the XL and XR, for example, they are the usual phase space variables. And as before, for example, given the phase space variable, the XL, I denote is the position and the momentum variable like this, and same as for the other phase space variable. And for the doubled phase space, we equip it with the symplectic form capital sigma defined like this, where the small sigma is the standard symplectic form on the single phase space. And with all this preparation, we can also define the symplectic Fourier transform of a function on the doubled phase space like this. All right, so to introduce the magnetic pseudo-differential super operator, we introduce the super file system, which is defined like this. Here, G is the magnetic pseudo-differential operator obtained by the quantizing the symbol G on the single phase space psi, and it's defined like this. So we take the action of the usual magnetic file system from simultaneously from left and right. Okay, and using this, we can define the magnetic pseudo-differential super operator in a similar way as in the magnetic pseudo-differential operator. So given a symbol, the capital F on the double phase space, we define the associated magnetic pseudo-differential super operator like this. Okay. And what happens if F is a function of the form like given as a product of the two functions with the phase space variable XL and XR? Well, in this case, then the symplectic Fourier transform on the doubled phase space is separated into the standard symplectic Fourier transform on the single phase space. So in this case, then this formula agrees with this formula. So in this case, the super operator can be seen as the simultaneous action of the two magnetic pseudo-differential operator from the left and the right. But we would like to deal with the symbol, the more general than just the product of the two, the symbol. And the Liouville superoperator has a symbol which cannot be seen as a product of the two symbols. So if the small h is a symbol of the magnetic Hamiltonian h hat to the a, then the double symbol defined like this is the symbol of the Liouville superoperator. Okay, so this is the kind of the formal derivation of the definition of the magnetic pseudodifferential superoperators. Now let me move on to so let me talk about some the rigorous analysis. So the first small result I'd like to mention is the mapping property of the superoperators on the space of bounded operators on Hilbert space and the Sutton P class of operators. Okay, so if we consider the Schwarz class symbol on the doubled phase space, then the superoperator associated with F induces a bounded linear operator on this space and the Sutton P class as well. So how do we prove that? Well, if for example, if G hat to the A is a Sutton P class operator, then this is the very definition of the magnetic the super Weyl system, and by the ideal property of the Sutton P class, we can see that this also belongs to the Sutton P class and satisfies this kind of estimate. Well, these two factors is one because the magnetic Weyl systems are all unitary. So by applying this estimate to the definition of the superoperator, then we can see that this integral can be estimated like this. So this gives the desired continuity and proves the second assertion. And the first assertion can be simply proved by replacing the Sutton P norm by the usual operator norm. All right, so now the next thing we wonder is that, so now we know that the superoperator assigns the operator to operators. And what the next thing wonder is that if the given operator is a magnetic pseudodifferential operator, then its image can be seen as a magnetic pseudodifferential operator. And if so, then what is the symbol? And by doing some computation, we could find the answer. And this proposition answers the above question. So if the f is the Schwarz class function on the doubled phase space and g is the Schwarz class function on the single phase space, then this magnetic operator mapped by this pseudo-differential superoperator can be seen as pseudo-differential operator associated with this symbol. And we can also prove that this symbol is also the Schwarz class function. And if the double symbol is of the product form, then the semi-superproduct reduces to the usual magnetic Weyl product from both sides. Okay, and the next question that we would like to deal with is the composition of two magnetic pseudo-differential superoperators. And we can see the composition of the two magnetic pseudodifferential superoperators as again the magnetic pseudodifferential superoperators, and this guy becomes its symbol. Okay, so assume if the magnetic field satisfies a polynomially bounded condition, then we can say that the super bioproduct of F and G defined like this also belongs to the Schwarz class function, and the composition of the two magnetic pseudodifferential superoperator again becomes the superoperator associated with this symbol. All right, and so far we have to deal with only the Schwarz class function, but we would like to extend the calculus to the symbols more general than the Schwarz class symbol. So the first step toward to extend the calculus is regard the semi-superproduct as the integral operator. So by doing some computation, it can be shown that the given f, which is a Schwarz class function on the doubled phase space, then this map can be seen as the integral operator associated with this kernel with this very cumbersome formula. And it can be shown that this map, assigning f to its kernel, can be decomposed into the partial Fourier transforms and coordinate changes, and multiplying the polynomially bounded functions, and all of them can be seen as an isomorphism on the Schwarz class function. So it can be shown that this map induces topological vector space isomorphism from the Schwarz class function to itself, and furthermore, all the maps I mentioned, the multiplication by the polynomially bounded function and the coordinate changes and partial Fourier transform, they can all be seen as the isomorphism on the space of tempered distributions as well. So it can also be shown that this map extends to isomorphism from the tempered distribution to itself. Okay, so how can we extend the calculus by using the previous lemma? Well, by doing some long computation, we could also prove this kind of formula. Here, the f to the t, the transpose of f means the function defined by the swapping the left and the right phase space variable. And by using the equality of these two sides, we can define the semi-superproduct of temporal distribution on the doubled phase space and the Schwarz class function G like this. Here it makes sense because if the f is the temporal distribution, then by this remark, the associated kernel is also temporal distribution. So we can make sense of this side. All right, so by using this definition, now we can define the thing which is called the magnetic semi-supermoyal space. So we say that the temporal distribution on the doubled phase space belongs to the magnetic semi-supermoyal space, which is denoted like this. If this map induces a continuous linear map from Schwarz space to itself. So, well, in this formula, if the f is a temporal distribution and the g is the Schwarz class function, then a priori, we cannot expect that the semi-product of f and g belongs to the Schwartz class function. This only explains that this semi-superproduct belongs to the temporal distribution. But if this map induces a continuous linear map from the Schwartz class function to itself, then we say that f belongs to the magnetic semi-super Boyle space. And with this definition, now we can define the product of the f, which is in the semi-super Boyle space, and the temporal distribution by using this formula. So by the very definition of the semi-super Boyle space, now we know that this guy belongs to the Schwartz class. So the right-hand side makes sense by the very definition of the semi-super Boyle space. Okay, so for the symbols on the doubled phase space, we introduced the two kinds of Fermander symbol classes. So if we want to take care of the order of the left and right variable separately, then we use this Fermander super symbol classes. But if we want to treat the kind of the merged left and right degree, then we use this Fermander, the symbol class. And unfortunately, it's tempting to think about the inclusion of these two symbol classes, but we found the concrete example that neither one of these can be included in another one, so we need to deal with them separately to prove the desired estimate. Okay, so by applying some oscillatory integral techniques, we could prove that both Fermander symbol classes belongs to the magnetic semi-super Boyle space, and the semi-super product of the doubled Fermander symbols and the single Fermander symbol enjoys this property. It gives this continuous bilinear maps. And what about the superproduct of Fermander symbols? Well, by using the similar duality technique I mentioned, like in this page, we could also define the subspace of the temporal distribution such that this product makes sense for all fg in this subspace. And we could also prove that this subspace is called the super Boyle algebra. And we could prove that by applying the oscillatory integral technique that these two doubled Fermander symbol classes belong to the super Boyle space, and the superproduct enjoys the decomposition property. And as done in the usual magnetic file calculus, we could also asymptotically expand the semi-superproduct in the small parameters epsilon and lambda, and we could also explain the superproduct as well. All right, so let me close my talk with some the future project we have in my mind. So, in the usual magnetic file calculus, there is a criterion using the commutators to determine whether a given operator is a magnetic pseudodifferential operator established by Iftimid, Mantoyu, and Friche in the 2010. So it would be nice if we could establish a similar criterion to determine whether a given superoperator is a pseudo-differential superoperator. And the last thing I'd like to mention is that, well, we desire to find the link of the newly developed pseudo-differential supercalculus to the algebraic setting. So given a symbol like this, well, the behavior of the x variable can be encode the properties of the given physical system. For example, if there is a periodicity in the given physical system, then the x part becomes a periodic function, and we could also implement the other properties of the system like this. And this can be taken into account by combining the coefficient to some C-star algebra. And it is also shown that in such case, the algebra of the pseudo-differential operator can be linked to the theory of the twisted cross-product algebra. So if we consider such a general coefficient case like this, then we would need to, where is it? Then we would need to consider the more general, the von Neumann algebra and the non-commutative LP spaces like this. So we wonder, for example, what would be the mapping property become in such a general coefficient case. So we would like to find the link to the algebraic setting. I mentioned it at the beginning of the lecture. Okay, so I stop here for today, and thank you very much for your attention.